Okay, today we are going to start with Maxima, Minima and the curve sketching. First, we start with the behavior of the derivative and the behavior of the function. How can we join these two things together? So the first theorem we are going to deal with is as follows. Suppose f is a function on the open interval ab to r. We assume that f is differentiable. So f is a function from ab to r. I assume that f is a differentiable function. Then the following thing is true, that f is increasing if and only if f prime x is bigger than or equal to 0 for all x in the open interval ab. We will see that one part of this result just follows from the usual definition of derivative of the function, and the other part uses mean value theorem, which we have proved in the last lecture. That is, you can think of this theorem as an application of the mean value theorem. So let's start with the proof of this function, of this result. Suppose that f is an increasing function. That is, if x1 is bigger than x2, then I know that fx1 is strictly bigger than fx2. Well, since I just said increasing, I did not say strictly increasing. I should say fx1 is bigger than or equals to fx2. Now if that is given, let x naught be an element in the open interval ab. Then I look at the definition of f prime at x naught. This by definition is limit x going to x naught plus fx minus fx naught divided by x minus x naught. Now notice that in the definition actually we have limit x going to x naught fx minus fx naught by x minus x naught, but since we are assuming that f is differentiable at x naught, one-sided limit is good enough to look at. So I have looked only at the right hand side. The meaning is that x approaches x naught from the right hand side of x naught. So in picture it will look something like this, that I have x naught here, x is here, it is going towards x naught. Now since I have that f is increasing, this would imply that fx minus fx naught is bigger than or equal to 0 as x is bigger than or equal to x naught. This would then imply that fx minus fx naught divided by x minus x naught, notice that x is bigger than or equal to x naught, so x minus x naught is also non-negative. This is bigger than or equal to 0. Since all the terms are bigger than or equal to 0, that would certainly mean that the limit, which is f prime x naught, is also bigger than or equals to 0. That is one part of the result. That is, we have assumed that f is increasing, and from that it follows that the derivative at any point x naught in that interval is also bigger than or equals to 0. Now we want to go about the other part. That is, it will be given to me that the derivative at each and every point is non-negative. From that I want to infer that f is increasing. Okay. So given that f prime at x is bigger than or equal to 0 for all x, in the open interval AB. So if I want to show that f is increasing, what I have to do is start with some x2 bigger than x1 such that x2 and x1 both are in the open interval AB, that is they are in the domain of the function, so that applying f on these 2 points do make sense. Now if I have this, what I have to do is I have to look at fx2 minus fx1. Somehow I have to show that this is non-negative. If I do that, it will prove that f is increasing. But at this point I can apply mean value theorem, which I have already proved. The statement of the mean value theorem says that f of x2 minus f of x1 is equals to x2 minus x1 into f prime at a point xi, where xi lies between x1 and x2. But by the given condition, I anyway know that f prime xi is bigger than or equals to 0. This then would imply that x2 minus x1, which is anyway non-negative because x2 is bigger than x1, times f prime xi, this is bigger than or equals to 0. But that would then imply that f of x2 minus f of x1 is bigger than or equals to 0. This implies f is increasing as x1 and x2 are arbitrary points in the interval AB. See, just for 2 points x1 and x2, if I check this inequality, that does not suffice that the function is increasing. So all we have to do is choose arbitrarily 2 points which I called x1 and x2, and then you try to prove that fx2 minus fx1 is bigger than or equals to 0, which I could do. That means f is increasing. Fine. That means to understand, given a differentiable function, whether the function is increasing or not, all I have to do is I have to check the derivative of the function at each and every point. If the derivatives turn out to be non-negative, then the function is increasing. And it is equally easy to show, which I will put as remark, if f from open interval AB to R is differentiable, then f is decreasing if and only if f prime x is less than or equals to 0 for all x in the open interval AB. The proof is exactly similar as the increasing case. Or what one can do is, given a decreasing function f, construct a new function g, which I will call minus f. Then that function will be increasing, and then the previous theorem can be certainly applied to it. Okay, but what about strict inequality? I will again put it as the second remark. If f prime at x is strictly bigger than 0, then f is strictly increasing. Follows again from the mean value theorem. Actually, it is if and only if. Well, this is not actually if and only if. If f prime x is strictly bigger than 0, then f is strictly increasing. It's very easy to prove. You just look at fx2 minus fx1, write it as x2 minus x1 times f prime xi then I know anyway this is strictly bigger than 0 by the assumed condition. That would imply that f of x2 is strictly bigger than f of x1. But what about the converse? Is it true that if f is strictly increasing, then its derivative everywhere is strictly bigger than 0? So the question is, if f is from AB to R and f prime x strictly bigger than 0 for all x in the open interval AB, is it true that f is increasing? The answer actually is no, and it can be shown by an example which we have dealt already with. So the answer is no. We look at the function fx equals to x cube, where minus 1 less x less 1. Then I look at the derivative f prime x, that is 3x square. It is bigger than or equal to 0. Actually f prime at 0 is 0. But what is the function? If I try to draw the graph of the function, it looks exactly like this. We will see after a few moments how do I draw the curve of this, but just assume for the time being that this is the curve of y equal to x cube, which can be shown. Then you can see that the function is strictly increasing. Nevertheless, at the point 0, the derivative is not positive, it is equal to 0. That means it can happen that even if you have a function which is strictly positive, differentiable, but at certain points its derivative can vanish. It is not necessary that derivative will be strictly bigger than 0. But the converse of this, that is, if you have a differentiable function whose derivative is always strictly bigger than 0, then the function is certainly strictly increasing. Okay. Now armed with this, let's observe something more which we have already seen. So I will call it a note. Suppose I have a function f defined on an interval AB. Assume f is differentiable. Let C is a point in AB which is a local maximum of f. Then we have proved in the previous lecture that then the derivative of the function at that point has to be equals to 0, and the converse is not true. It is again given by the previous example, y equals to x cube. I can look at the function y equals to x cube, its derivative at 0 is 0. But if you look at the graph of the function y equals to x cube as drawn here, the point 0 is neither a local maximum nor a local minimum, but its derivative is 0 there. That means the derivative of a function at a point being 0 does not guarantee that the point is either a local maximum or a local minimum. So the question we are asking now, that what other condition we can put on the derivative which will guarantee that the point is either a local maximum or a local minimum. Well, it turns out that staying just within derivative, it's not that neat. One has to go to the double derivative. That is the thing we are going to try now. So let's first observe the following thing, which I will call a lemma. Let be a function defined on the open interval AB to R and C belonging to AB. Now suppose if there exists delta bigger than 0 such that A is less than C minus delta, B is bigger than C plus delta, F is increasing in C minus delta C and decreasing in C plus delta, and F continuous at C, then C is a local maximum for F. So let's just draw a picture which will help us understanding the statement clearly. So this is A, this is B. Now this is C, this is C minus delta, this is C plus delta, and on C minus delta C the behavior of the function is that it increases, and on C plus delta the behavior of the function is it decreases. Then it is believable that at the point C the function is having the local maximum, but this needs to be proved now. So this is how we go about it. Let x1 satisfy C minus delta less x1 less C. Then I can say that if x1 is certainly less or equals to limit x going to C minus fx. Why so? Because when I look at x going to C minus, it means that I am approaching C from the left hand side. Now if you think in terms of the sequence, the corresponding values for all these fx's are increasing, because I said that on C minus delta C the function f is increasing. Now the sequence then will converge to the supremum, which has to be anyway strictly bigger than or equals to f of x1. That is what is written here. But now I can use the fact that f at C is continuous. That means this is equals to fc. That means if I choose any x1 in C minus delta C, f of x1 is less than or equals to fc. Similarly, if x2 satisfies then I know that f of x2 has to be bigger than or equals to limit x going to C plus fx, which again by continuity is equals to fc. This implies that C is a local max. Now again, as remark, I will tell you what happens in the case of minimum, that if f is decreasing in C minus delta C and increasing in C plus delta, then C is a local minimum. Of course, our assumption is f is continuous at C. Now this result has an interesting corollary. Now the corollary is that suppose f is from AB to R, f is differentiable and C belongs to AB. If f prime x is bigger than or equals to 0 for all x in C minus delta C, and f prime x is less than or equals to 0 for all x in CC plus delta, then C is a local max for f. It actually follows from the previous result which we have done. Proof is very simple, that the given conditions imply that f is increasing in C minus delta C and is decreasing in CC plus delta. Then I can use the previous lemma, which would imply that C is a local maximum for the function. Now this can be used in the next theorem, which is the very useful one, and time and again we apply that. So this I will mention as a theorem. This is usually called the double derivative test of maximum and minimum. So let f is from a b to r again. Differentiable, and if double prime C exists, if prime C is equals to 0 and if double prime C is strictly less than 0, then C is a local maximum for f. So the point is that I have defined a function f on the open interval AB. Suppose there exists a point C where f prime C is equals to 0. If f is twice differentiable at C and the double derivative of f at C is less than 0, strictly less than 0, that is important, then C turns out to be a local maximum for the function f. Well, let's go for the proof of it. Most of the time while talking about maximum and minimum, we only talk about this result, but notice here one thing, that the point C where we are testing for the maximum and minimum, that point C is an interior point of the interval AB. That is, C is not an endpoint of the interval. That means if you have function whose maximum and minimum occur at the endpoints, for those cases this theorem will not apply. This theorem applies only in the case when you are searching for maximum minimum in the interior of the interval where f is defined. Well, now since if double prime C is strictly less than 0, we have by definition limit x going to C f prime x minus f prime C divided by x minus C to be less than 0. This is the definition. This implies there exist delta bigger than 0 such that for all x in C minus delta C union CC plus delta, we have that f prime x minus f prime C divided by x minus C is less than 0. Now let us look at the cases when x belongs to C minus delta C. What does it mean? Now x belongs to C minus delta C. Let us look at this case first. This implies f prime x, I can forget f prime C because f prime C is 0, that is one of my assumption, divided by x minus C, this is less than 0. Now what does this mean? Because x is in c minus delta c, this implies anyway that x minus c is less than 0. That means the denominator here is less than 0. The total quantity is anyway less than 0. That means the numerator has to be positive or at least non-negative. This would then imply that f prime x is strictly bigger than 0. So if x is in c minus delta c, that means f prime x is strictly bigger than 0. But this then implies that f is increasing in c minus delta c. On the other hand, if I choose x in c plus delta, notice that this would imply that x minus c is strictly bigger than 0. Then again, from the condition on the double derivative, I have that f prime x divided by x minus c is strictly less than 0. That anyway is given to me. Now I have the numerator and the denominator, and the denominator is positive but the whole quantity is negative. That would then imply that the numerator, that is f prime x, this must be strictly less than 0, which then implies that f is decreasing in c plus delta. So the situation is, I have the point C. On c minus delta c, f is increasing. On c plus delta, that is on the right hand side of c, f is decreasing. But then in the previous case we proved that if f is continuous at c, that means c is a local maximum. But f is differentiable at c, so it is certainly continuous. So this would then imply by a previous lemma that c is a local maximum. Analogously again, I can deal the case of minimum, that is given as that f is from AB to R, differentiable if C belongs to AB with the condition f prime C is equals to 0, and if double prime C exists and positive, then C is a local minima for F. Now let us look at the following example. Fx is equals to x if x belongs to closed interval 1, 2. You see that f is a nice differentiable function. I can easily draw the graph of the function also, that this is the point 1, this is the point 2. At the point 1 the value of the function is 1, at the point 2 it is 2, so it looks like this kind of. You can see that the point x equals to 2 is the maxima. But if I look at f prime x, that is continuously equals to 1 for all x, it's a constant function 1. So f prime 2 is not equals to 0. But I said that if you have a local maximum, then at that the function has to be equals to 0. X equals to 2 is a local maximum for the function, but the derivative is not 0. Why is it happening? Well, if you look back at the proof of the theorem where we have proved that at the local extremum the derivative of a function is 0, it assumes that the point which we are looking at, that is the extremum, the maximum or the minimum, whatever you say, that point has to be in the interior of the domain of definition of f. That is, it cannot be a boundary point. But look at the situation here. I have my function fx equals to x. The maximum is happening at the boundary point x equals to 2, and that is why the derivative is not equals to 0. If you notice, the same thing is happening at the minimum also. X equals to 1 is the minimum of the function, and it is attained at the end point 1, which is not in the interior of the function, and hence the derivative at 1 is also not equals to 0. Well, now you might say that, well, I might increase my intervals a little bit, that is, I look at 1 minus epsilon and then increase this to 2 plus epsilon. Then the point 2 is an interior point, but the derivative is not 0 there, which is obvious now, because if x is equals to 2, then fx is neither maximum nor the minimum. It ceases to be the local extremum, and hence the derivative is not 0. So no contradiction in the previous theorem, but this is just to remind you that you have to be very careful about the situation of the local maximum or the local minimum. If it is not in the interior, none of the theorems which we have proved so far works. At the boundary points, the theorems do fail. Now we want to talk about something called convex functions. We will first start with convex combination of points. The question is this, that suppose I have the real line, this is a point x1, this is a point x2. Now if I look at an x3 which satisfies that it is bigger than x1 and it is less than x2, then is there any way of expressing the point x3 in terms of x1 and x2? So question is, can we write down x3 in terms of x1 and x2? Well, it turns out to be the answer is that there exists then a t in the open interval 0, 1 such that x3 equals to tx1 plus 1 minus tx2, which I leave as an exercise for you to verify that given any x3 between x1 and x2, there exists a t in the open interval 0, 1 such that x3 is tx1 plus 1 minus t into x2. Well, if x3 turns out to be equal to x1, then what you do is you just take t to be equals to 1. So if t is equals to 1, then x3 is equals to x1, and if t is equals to 0, then x3 is equals to x2. The same thing works in the Cartesian plane also, that if I have 2 points xy and x1, y1 in R2, then the points of the form t times xy plus 1 minus t into x1, y1 represents points on the line joining xy and x1, y1. Now with this preparation, we come to the definition of convex functions. So this is the definition of convex functions. Suppose f is a function on the open interval AB to R. It might be closed interval also, but open interval suffices for us. Then F is called convex if given any x and y in the interval AB, f of tx plus 1 minus ty is less or equals to t times fx plus 1 minus t times fy. Well, let us try to understand the meaning of this. First, let us look at the quantity tx plus 1 minus ty. What does this mean? It represents the points on the line joining at x and y. That means it is all the points between x and y. If I look at the right hand side, that is here, it represents all points on the line which joins fx and fy. So in the picture, then what should it mean? I draw the axis. Let us say this is x and this is y. Then tx plus 1 minus ty represents points between x and y. Now, let us say this height is fx, and let us say this is fy. Now then, if I look at the right hand side of the above inequation, the right hand side actually represents the line joining fx and fy. Now the definition of the convex function says that if I take any in-between points, for example if I take z here, then fz should be lying below the above line, that is fz should be somewhere here. That is, it is saying, the given definition is saying that the graph of the function then must look like this. That is, given any 2 points, you look at the graph of the function, then at the points xfx and yfy, look at those 2 pair of points, join them by a line, then the graph of the function lies below that line. That is what the definition of convexity says. Now just in this form, it might become a bit difficult to understand which functions are actually convex. So to understand this criteria and to make it more applicable, what we do is we assume differentiability of the function, and we try to devise a criteria involving differentiability which will produce the convexity of the function. So that is our aim in the next theorem. Now let's first observe the following thing about derivatives of functions. So I will call it a little lemma whose proof is very easy. Suppose f from c to d to r a differentiable function, and let a belongs to cd, and also suppose that if double prime a exists. So we are saying that f is a differentiable function in CD, a is a point in CD, and the double derivative of f at a exists. Then the following is true. Then f double prime a is equals to limit h going to 0, f of a plus h plus f of a minus h minus twice f a divided by h square. Now this is a lemma which we are going to use in our device of convexity of a function using derivatives. So the proof goes as follows. What I do is I look at the function gh equals to f of a plus h plus f of a minus h minus twice f a. Then we need to prove that limit h going to 0, g of h divided by h square is equals to f double prime a. Now if you just think naively that putting h equals to 0 in the numerator and denominator, you quickly observe that this is a famous 0 by 0 form, and as we have done in the last lecture, to take care of the 0 by 0 forms you use the L'Hopital rule. The condition is for the L'Hopital rule that the both functions has to be differentiable, certainly. Second one is that the denominator, if h is not equals to 0, should be not equals to 0. Well, that is the case. H square is always not equals to 0 if h is not equal to 0. So what I can do is I can write that limit h going to 0, g of h divided by h square is equals to limit h going to 0, g prime h divided by twice h. This is by L'Hopital rule. Now let's calculate g prime h. How to do that? Well, we will just use the chain rule here, that g prime of h is first f prime at a plus h and then the derivative of f plus h as a function of h, which is 1. So this is into 1 plus f prime at a minus h into derivative of a minus h as a function of h, which is minus 1. The rest is constant. Twice f a does not involve h, so the derivative is anyway 0. So what we get is that limit h going to 0, g prime h by twice h is same as limit h going to 0, f prime at a plus h minus f prime at a minus h divided by twice h, which now we write as limit h going to 0, f prime at a plus h minus f of a plus f of a minus f prime at a minus h whole divided by twice h, which is same as f prime at a plus h minus f of a divided by h plus limit h going to 0, f of a the whole thing I will put a half outside. Now look at the two individual limits inside. The first limit is certainly f double prime A, but so is the second one. So this is also F double prime A, and then I have a half outside, that is F double prime A. This proves our lemma. Now using this, we are going to prove the next result, which is the most fundamental result for applications as far as convex functions are concerned. So the theorem is this. Suppose f is defined in an interval I to R. Suppose this is twice differentiable. Then f is convex if and only if double prime at every point of the interval I is bigger than or equals to 0. Well, right now we are in a position to prove only one part of the theorem. For the other part, we will need something called Taylor's theorem, which we are going to do next. But let's prove only one part of this theorem and then apply it to draw some curves of functions. So the proof of this goes as follows. So assume that f is convex. We are going to prove that the double derivative of f is non-negative. Well, let A be an arbitrary point in the interval I. All I know is f double prime at A, I have to prove that f double prime at A is bigger than or equals to 0. I have just assumed that f is convex. I have taken a point A in I. I need to prove that f double prime of A is bigger than or equals to 0. Now since I is an open interval and A is in I, this implies there exists H such that these 2 points A plus H and A minus H both are in I. That means this whole interval A minus H and A plus H both are contained in I. Now I can certainly write A to be equals to half A minus H plus half A plus H, because A is the midpoint of A minus H and A plus H. Notice that then this is a convex combination. Since f is convex, it would imply that f of A, which is equals to f of half of A minus H plus half of A plus H, is certainly less than or equals to, by definition of convexity, it is half of f A minus H plus half of f A plus H. If I multiply this inequation by 2 on both sides, this would then imply that f of F plus H plus f of A minus H minus twice f of A is bigger than or equals to 0. Now this would then imply, if I divide by H square, which is anyway non-negative, that f of F plus H plus f of A minus H minus twice f A divided by H square is also bigger than or equals to 0, as H square is bigger than or equals to 0. Now since this is true for all small h, this would certainly imply that limit h going to 0, f of f plus h plus f of a minus h minus twice f a divided by h square is bigger than or equals to 0. But now recall the previous lemma where we have proved that this limit actually is f double prime a. So this would then imply that f double prime a is bigger than or equals to 0. Now I will just remark here so that you can remember the converse of this will be proved later using something called Taylor's theorem. That means, assuming that using Taylor's theorem we can prove this, it means that if I have a function defined in an interval which is differentiable twice and the double derivative is everywhere non-negative, that means the function is actually a convex function. Now then it becomes very easy to give examples of convex functions that you can see very easily. I can say fx that is equals to e to the power x. Okay, fx equals to e to the power x is convex because double derivative of f is e to the power x, which is bigger than or equals to 0. For example, if I look at fx equals to x to the power n, where n is bigger than or equals to 2 and x is bigger than 0, then f is convex because the double derivative of f is n into n minus 1 into x to the power n minus 2. Since n is bigger than or equals to 2, this quantity is always non-negative because it is power of x and x is positive, so the function is actually convex. So using this theorem we can very easily detect if the function is twice differentiable, whether it is convex or not. Now similarly I can talk about concave function also. We will just define it by saying that f is concave if minus f is convex, which you can check easily that the inequality which defines convexity, it will go on the reverse side for concave functions. So a typical way of looking at convex functions would be something like this, to remember that this is a convex function. And if I want to talk about concave functions, it would look something like this, because if you take the points here and here, look at the line joining these two, the function lies above the line. This means concave. And here the situation is, if I take this point and this point, join the line, the graph of the function lies below the line. That means this is convex.